The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Now let's shift our attention towards the electron configuration of ions. Now recall, to gain an outer noble gas configuration, positive ions, that being cations, are formed by removing an electron from an atom, whereas negative ions, that being anions, are formed by adding electrons to an atom. Now, we'll take a look at two examples, sodium for our cation and then chlorine for our anion. Beginning here with sodium. We see here a sodium atom is going to have an electron removed, a valence electron removed from a 3s orbital, and forming a sodium cation, which has the electron configuration of 1s2, 2s2, 2p6. Whereas for chlorine, see here an electron is added to a chlorine atom to form a chlorine anion that has a new electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and that electron is added to the valence electrons to achieve that octet arrangement. Now, we can make a more general statement and say that main group metals such as sodium, they are going to have their electron removed from the highest energy occupied orbital, whereas non-metals such as chlorine, they have their electron removed from, they have an electron added to the lowest energy unoccupied orbital. So the electron being removed comes from the highest energy occupied orbital. Electron being added goes into the lowest energy unoccupied orbital, as we see here. Now, for moving on, for transition metals, the first electron that's being removed is not always going to be coming from the highest energy occupied orbital. It's going to be a little bit different. Let's take a look at that now on the next slide. For transition metals such as iron, as we see here, the first electron being removed is going to be the valence electrons, even though the 3d electrons are added after to the 3d subshells. Now, another way we can say this, and this is very important for you to remember, that the first electrons being removed are being removed from the orbital with the highest principal quantum number. Now, for the electrons closest to the valence shell, such as the ones here in the 3d subshell, they too can be removed, but only after the valence electrons have been removed. For example, iron here, it has two valence electrons. Once these two valence electrons are removed, then the iron atom, the iron cation, can have the 3d electrons removed, as we see here. Now, in summary, it's important for you to remember that for transition metals forming cations, the valence s shell electrons are going to be removed first, then the d electrons. So once again, valence shell s electrons removed first, then the d electrons. Okay, let's proceed to our next slide here. And again, we have two more examples here of transition metals, that being titanium and manganese. And we see here, once again, valence shell s electrons are removed first, then the d electrons. And for manganese, valence shell s electrons removed first, as we see here as well. Okay, great. Let's proceed to our next slide. Now, a term that we should be comfortable with is isoelectronic. Now, when different atoms or ions have they're going to have the same number of electrons and have the same electron configuration, they're then said to be isoelectronic. Now, let's go ahead and read our definition. Having the same number of electrons and the same electron configurations. Let's do an example here. What neutral atom is isoelectronic with a hydride ion? Now, if we take a look here, we see that the hydride ion has 2 electrons, so does the neutral helium atom. Thus, we can then say that the hydride ion is isoelectronic with helium. Okay, great. Let's proceed to our next slide. Now we'll do a quick example here on isoelectronic. Which of the following ions are isoelectronic with neon? In A, is it the sodium ion, or is it the sodium ion and the fluoride ion in B, or C, the sodium ion, the fluoride ion, and the oxide ion, or in D, sodium, fluoride, oxide, and the nitride ion? And if let's go ahead and call upon our periodic table. Let's begin by highlighting all the elements here of interest. So we have our sodium, we have our fluorine, we have our oxygen, and we have our nitrogen, and we'll highlight neon here in green, as that'll be our reference element here. Now first we have our sodium atom that loses an electron to become a sodium cation. Now if our sodium atom, as we see here, if it loses an electron, it will have the noble gas configuration of neon. Thus we can say that the sodium ion is isoelectronic with neon. Fluorine, similarly, a fluorine atom is going to gain an electron to become a fluoride ion, as you see here. And when the fluorine atom gains an electron, it too will have the noble gas configuration of that octet arrangement here of neon, right? Thus, we can then say that fluorine is isoelectronic with neon. How about oxygen? When the oxygen atom gains 2 electrons to become an oxide ion, it too will be isoelectronic with neon. And the nitrogen atom, when the nitrogen atom is going to gain 3 electrons, 1, 2, 3, to become a nitride ion, it too will be isoelectronic with neon. Thus, in this scenario, we can then say D is the correct answer choice, as all of the following ions are isoelectronic with neon. Let's proceed now to our next slide. Now here we're being asked